Hello, everyone. We're going to be focusing on how to make Lewis structures and identifying nonpolar versus polar molecules. This video will cover topics such as resonance structures, formal charge, and VSEPR. So, what are Lewis structures anyway? Lewis structures are used to show valence electrons in a molecule. We would need to know the central atom, the total number of valence electrons, and brackets if the molecule has a charge to make a Lewis structure of our own. Our first Lewis structure is going to be silicon dioxide. First, we will need to know the total number of valence electrons. Using the periodic table, we can see that silicon has 4 valence electrons, and oxygen has 6 valence electrons per oxygen atom. So the total number of valence electrons will be 16. Next, how do we determine our central atom? Our central atom is usually the atom with the lowest subscript in the molecular formula, or the atom that can form the most bonds, and the least electronegative atom. In this case, silicon is our central atom. First, you assign your lone pairs to the oxygen atoms, then start with single bonds between the silicon to both oxygen atoms. This gives us 16 valence electrons, right? You're probably wondering why silicon does not have 8 valence electrons surrounding it. And that's because central atoms in groups 3 and up will violate the octet rule, which includes silicon in group 3 on the periodic table. So how do we check if our Lewis structure is correct? Formal charge. You calculate the formal charge by subtracting the number of lone pair electrons and subtracting the number of lines of bonds from the total number of valence electrons of the atom. For instance, silicon has 4 valence electrons, so we'll start with 4, minus 0 lone pair electrons minus 2 lines from the single bonds. So this would look like 4 minus 0 minus 2, which gives us positive 2. Then for the oxygen atoms, we'll start with 6 valence electrons minus 6 lone pair electrons minus 1 line from the single bond with silicon. This will give us negative 1. You might be thinking that this is okay since it gives us a net formal charge of 0, but we want the Lewis structure with the lowest charges on each atom. So what we'll do next is we'll move 1 lone pair from the oxygen atom, or each oxygen atom, and create double bonds with silicon. So now when we calculate the formal charges for silicon in both oxygen atoms, we'll have a net charge of 0. In this case, we will only have 1 Lewis structure or 1 resonance structure for silicon dioxide. Resonance structures is simply when a molecule has more than one possible Lewis structure, or in other words, a different arrangement of valence electrons. Resonance structures show us that electrons within a molecule are delocalized, meaning that they can flow freely through the molecule. The example shown is thiosulfate with a negative charge of 2. The dotted lines on the Lewis structure simply show or represent the different resonance structures possible. It might seem a bit confusing, but the dotted lines show that there could be a double bond on any 2 atoms in a single Lewis structure. To have a better visual of different resonance structures, the nitrite ion example shows how double bonds can occur on the different oxygen atoms. Okay, so we figured out how to write a Lewis structure and the importance of resonance structures and formal charges. But how do we figure out a nonpolar or polar molecule? So it's called the VSEPR chart, or standing for valence shell electron pair repulsion, which is a model used to predict 3D molecular geometry based on the number of valence shell electron bond pairs among the atoms in a molecule. So what does a VSEPR chart tell us? So every time you make a Lewis structure, it tells you 2 things: your electron geometry and your molecular geometry. So your electron geometry is the number of electron groups around your central atom, and your molecular geometry is the number of lone pairs around your central atom. So let's look at these examples to see how this makes sense. So let's start with NH3, ammonia. Looking at our central atom, we're going to count our electron groups, which includes our lone pair electron groups and the number of bonds. So we have 3 bonds with 3 different hydrogen atoms, plus 1 lone pair electron group. So that's 4 for our electron geometry, which gives us tetrahedral, looking at our Vesper chart. To determine the molecular geometry, we just need to figure out how many lone pair groups we have, which is just 1. So looking back at our chart, trigonal pyramid is our molecular geometry for NH3. Our second example, H2O, our central atom has 4 electron groups. So again, giving us tetrahedral. But this time we have 2 lone pair electron groups. So our molecular geometry will be bent. Moving on, hydrogen fluoride. The central atom in this case is hydrogen, and it just has 1 electron group, which would be linear. Because there are no lone pair electrons for hydrogen, there won't be any molecular geometry. And also, if you look at your Vesper chart, you will also see that the only molecular geometry possible for a linear electron geometry is linear. So, what does the molecular geometry tell us about a molecule being polar or nonpolar? So, to keep it short, symmetrical molecular geometry gives us a polar molecule, and asymmetrical molecular geometry gives us a nonpolar molecule. So if we go back to NH3 having a trigonal pyramid geometry, that is an asymmetrical shape, which means that NH3 is a nonpolar molecule. And with H2O having a bent molecular geometry, which is also asymmetrical, it means that that is a nonpolar molecule. And lastly, with our hydrogen fluoride, we saw that it had 0 lone pairs on the hydrogen, and we had a molecular geometry of linear, which is actually symmetrical, different from the other 2 examples. And this tells us that it is a polar molecule. So usually when you have a molecular geometry with 0 lone pairs being linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral, these are all symmetrical molecular geometry shapes that will give us a polar molecule. But also, square pyramid is another example of a symmetrical geometry that can give us a polar molecule. This will be our only exception. Other asymmetrical shapes on the Vesper chart will give us nonpolar molecules. Now we know how to make Lewis structures and determine whether a molecule is polar or nonpolar. Before, we were just familiar with observing the electronegativity differences. Thanks for watching.